Hello everyone, this is discussion for March 19th. So again, I'm sure everybody knows, but if you don't, face-to-face classes have been canceled for the rest of the semester. So for the rest of the semester, all assignments should be turned in by email and my email address. And make a scan or take a picture of handwritten solutions and email by the due date. Adobe Scan is a nice app for doing that. The assignment for 8.2 will be due on Tuesday. Okay, not today, on Tuesday, if you need more time. I'm going to go over a little bit of the information for that as well today. And 8.3, that'll be due Thursday next week and Tuesday the week after that. And then we'll have an exam on sections 8.1 to 8.4 on Thursday, the 2nd of April. Okay, so that is 2 weeks from today. Extra problem for grad students are posted. So let's go over some information for the problems in section 8.2. All right. So in section 8.2, all right, number 18. So assignment for section 8.2. So number 18, you should have enough information to handle this question. Number 24, this was discussed Tuesday. Well, it's discussed in the lecture for section 8.4. We discussed exactly this problem and how to solve it. So you can, if you want to look at the video, it's the lecture for section 8.4, video part 1. And we'll do part 2 of that today. And then 29, which says, let n be a normal subgroup of G such that n is cyclic. Okay, prove that H is a normal subgroup of G where H is any subgroup of N. Okay, so any subgroup of a normal, any subgroup of a normal cyclic subgroup of G is going to be normal again. Now that's not true in general at all for just general subgroups, but with cyclic subgroups it does work. Turn that off. Okay, for number 29 you'll need the following facts. Right here. If H is a subgroup of cyclic group, so we'll call it A. Then H is also cyclic. So any subgroup of a cyclic group is still cyclic. And we'll just do finite. Let's say it that way. Any subgroup of a cyclic group then H is cyclic as well. Okay, proof, we'll just do the proof for finite groups. Okay, so say that H is a subgroup of A, which is a cyclic group of order n. Right. So H is a subgroup of a cyclic group of order n. So the elements of H are all powers of A. Say that A to the K is an element of H is the smallest positive power. Right, you don't have negative powers, but you know, 1 is A to the 0, of course, right? So say A to the K is the smallest positive power of H, of A in H. Well, yeah, it could be that H is just the identity element. That's a subgroup. It could be that H is just the identity element, which is a subgroup, and that, of course, is cyclic, but, I mean, that's not, you know, that's not worth belaboring, so we'll just assume that it's not just the trivial group. Okay, so say that A to the K is the smallest positive power in A of A and H. Now, by closure, right, A to the mk, right, which is equal to A to the K to the m, is an element of H for all m in Z, right? So the cyclic subgroup generated by A to the K is a subgroup of H, right? I mean, you know, the product of any two elements in H has to be in H because it's a subgroup. So any power of A to the K itself is also in the subgroup. So we have that A to the K is a subgroup of H. We want to show that that's actually all of H, all right? So now take any other A to the what? A to the P in H. We'll show that K divides P. So that K divides P which will then imply that A to the K actually equals H, right? So the powers of A to the K, which is A to the, right, A to the mk are the powers of A that are multiples of K, right, which is A to the K to the m. That's all the elements of H. If we can show that K divides P. Okay, so that's what we're going to do. Well, by the division algorithm, right? By division algorithm, THM, P is equal to KQ plus R, where 0 is less than or equal to R is less than K. Right? Oh, am I using, that's a bad letter. P, K, A to the S. P stands for prime usually, right? All right, S. So we want to show that R is equal to 0. Right? If R is equal to 0, then we're done. Well, let's not say it that way. Okay, so A to the S, which is equal to A to the KQ plus R, is equal to A to the KQ plus, or not plus, times A to the R, where this is in H. And this is in H. Right? So A to the S times A to the minus KQ is equal to A to the R. Right? Where these guys are both in H. Right? So A to the R is an element of H. But R is less than S, which was the smallest power of A in H. So smallest positive power of R in H, of A in H. Smallest positive power of A in H, and R is less than that, so R has to be 0. So by the minimality of S, R is equal to 0. So A to the S equals A to the KQ as required. Okay, so that's the proof of this theorem here. But that theorem is needed for number 29. Okay, so number 29. Let N be a normal subgroup of G such that N is cyclic. Prove that H is a normal subgroup of G, where H is a subgroup of N. So any subgroup of a normal cyclic subgroup is normal. Okay, and in order to prove that, you'll need if H is a subgroup of a cyclic group, then H is itself cyclic. Okay, so there's the proof of that. Okay. The homework assignment for section 8.3. So this assignment is due on Tuesday, okay? And, I'll be available for discussion on Monday, and I can talk to you other times if you'd like as well. Contact me by email. And we can set up a time to do it. But I'll be available for discussion on Monday. So let's let's try to make sure that we understand these problems. Okay. Okay. So section 8.3 assignment for 8.3. All right, so 8.3, number 8. All right, you're trying to show that Z4 cross Z4 mod the cyclic subgroup generated by 3,2. Is isomorphic to Z4. Okay, so all you need to do is to calculate the order of Z4 cross Z4 over 3,2, right, which is equal to the order of Z4 cross Z4 divided by the order of the element 3,2, which is the order of the cyclic subgroup generated by that guy. You want to calculate that, make sure it's 4, and then show that Z4 cross Z4 over that has an element of order 4. All right, so you want to show that the order of this guy is 4 and has an element of order 4. And that will show that it's Z4. Just a cyclic group of order 4. The cyclic group of order 4, it's always Z4. Cyclic group of order n is always Zn. And that's number 8. Number 14, that's self-explanatory. It's just a calculation of S4. So calculate the multiplication table for S4 mod V. So they give you S4, and then V is a subgroup of order 4. Normal subgroup of S4. And then, so S4's got order 24. This guy's got order 4. So 24 over 4 is 6. So that's going to be a group of order 6. And, you're just going to calculate the multiplication table for it. Keep in mind that, there's only 2 groups of order 6. Right? There's S3 and Z6. The cyclic group of order 6. And then S3, or the symmetries of the triangle. Okay? So that'll help you construct that table. You're going to have to get something isomorphic to one of those 2 groups. Number 16, this is like number 15, which was an example from the March 12 discussion. Okay? And number 24, again, use the fact that any subgroup of a cyclic group is, again, well, actually, does it need that? No, actually, it does not. Does it need that? No, it doesn't need that. I'm sorry. I thought it did, but it doesn't. All right, it's all you need to do is just consider the smallest power of the generator of G that falls in. So you're trying to show, so if G is a cyclic group, and N is a normal subgroup. Well, any subgroup. So G is a cyclic group and N is any subgroup. And you're trying to show that G mod N is cyclic. G mod N is cyclic. Well, to show that G mod N is cyclic, just consider the smallest power of the generator of G. So G is, it's a cyclic group, so it's got some generator, and some power of that's gonna enter into N, and that will think about that, and that should answer the problem for you. Okay. All right. One more item I would like to talk about is the following facts. Classifying groups of small order. Okay, so group of order 2. So groups up to isomorphism. So order 2, there's only Z2, right? Actually. And so if P is prime, so if P is prime and the order of G is P, then G is isomorphic to ZP. Alright, so, that's one fact we had already. So, for groups of order 2, there was Z2. For groups of order 3, there was Z3. For groups of order 4, there was Z4 and C2 cross Z2. All abelian so far. Groups of order 5, just Z5. Groups of order 6, so first non-prime there. Well, aside from 4, first non-prime that doesn't have just abelians. There was Z6 and S3, which is the same as D6. Order 7, there was Z7. Order 8, well, we haven't talked about that yet, but there's 5, 3 abelian, 2 non-abelian. So the 2 non-abelian, that was the symmetries of the square and that quaternion group. We didn't actually prove this one yet, but we've kind of been using that fact. We've mentioned it several times. And then 9. Okay, so that's P squared. That's 3 squared. And then here, there's only going to be Z9 and Z3 cross Z3. So the theorem is as follows. If the order of G is P squared, then G is isomorphic to ZP squared, is cyclic, or ZP cross ZP. We can't prove this. So groups of order 9, groups of order 25. What's next? 49. Did I miss one? 3, 25, 7, 49, 9, 11, Z131, or 121, sorry. Groups of order 121, there's Z11 and Z11 cross Z11. Anyway, it's a nice fact. We can't prove this completely, but we can prove part of it. And I'd like to actually do that right now. So let's prove part of this fact. So if the order of G is equal to P squared, then G is isomorphic to ZP squared or ZP cross ZP. Okay, partial proof. We will be able to do the proof later, but we can delay that later part and do the rest. Okay, partial proof. So we proved the theorem in class that if G mod the center of G is cyclic, then G is abelian. Right? The center, it's the set of all elements in G that commute with all other elements. And if G is non-abelian, then G mod Z can't be cyclic. Or if G is cyclic, then G mod Z is cyclic, then G is abelian. If G is non-abelian, then G mod Z is cyclic, not cyclic. Okay, that's the original statement in the contrapositive. All right, so we will prove in chapter 9 somewhere. So later in the semester, we will prove that. And it's not hard, it just needs some facts that we haven't covered yet. Standard facts. We will prove that if the order of G is P to the M, just power some prime, then the center of G is not 1. So any group that has order power of a prime, so order 2, order 4, order 8, order 16, 32, 64, order 3, order 9, order 27, order 81, order 243, order 5, 25, 125, 625, so on and so forth. Any group that has prime power order does not have a trivial center. The center has to have stuff in it aside from the identity. Okay. So later in the semester we will prove that. So if the order of G is equal to P squared, then the order of ZG is equal to P or P squared. Okay, because the order of a subgroup because of Lagrange's theorem. The order of a subgroup divides the order of a group. Okay, so it's either 1 P or P squared, but by this theorem up here, it's not 1. So it's either P or P squared. Right? So if the center of G is equal to P squared, then the center of G is equal to G, so G is abelian. Right, because the center of G, it's the set of all elements in G that commute with everything. It's the set of all A in G, such that AB is equal to BA for every other B in G. So, that definition tells you if the center is the whole group, then it's abelian to begin with. If the order of ZG is P, then G mod ZG has order of G over order Z, which is P. But the only groups of order P a prime are cyclic. Then that group is cyclic. Right? That's the theorem right here. If G mod ZG is cyclic, then G is abelian. Well, here G mod ZG has got order P, and the only groups of order P are cyclic. Right? So G is abelian. Right? So far we've got that G is abelian. Now, G is abelian. And if G has an element of order P squared, then G itself is cyclic. Okay. If G does not have an element of order P squared, so if every non-identity has order less than P, or less than P squared, then the order of G is equal to P for all non-identity G and G, right? Because the order of an element or the order of a subgroup has to divide the order of a group. There's only two divisors of P squared, or three divisors of P squared, 1, P, and P squared. So if you're non-identity, it's not 1, and if we assume there is nothing of order P squared, then it's got to be P. So every element in G has order P. All right, take two elements in G. Such that B is not an element of the cyclic subgroup generated by A. The cyclic subgroup generated by A only has P elements in it, but G has P squared elements in it. So there's got to be some B that's not in there. Okay, since P is prime, the cyclic subgroup generated by A and the cyclic subgroup generated by B intersect in just the identity. Right? This is because every non-identity element of A has order P. Right? Every element of the cyclic subgroup generated by A, which has order P, also has order P. Because it has to divide P, but nothing divides P except 1 and P. So everything in here has order P. Everything in here has order P. So if they overlap, by closure, they got to be the same. So they're actually different. So now, the set of all A to the I, B to the J, such that 0 is less than or equal to I and J is less than, or I should say it that way, such that I and J are elements of the set 0, 1, 2, 3, up to P minus 1, right, is a subgroup of G of order P squared. Right? Because the powers of A and the powers of B have no overlap. Right? And you have to prove it's a subgroup. It's no big deal. Because G is commutative, this is, well, actually that was a homework problem. Yeah, that was a homework problem, I think, way back when. That's the case. Yeah. Like in section 7.2, I believe that was a homework problem, something similar to that. It's a subgroup of G of order P squared, so it's actually all of G. G, is equal to the set of all A to the I, B to the J, such that I, J are elements of 0 to P minus 1. Okay, but, using the function f from G to Z P cross Z P, given by f A to the I, B to the J, equal to just the pair IJ. Okay, we can show, well, not using the function, so we can show that the function, f from G to ZP cross ZP given by this is an isomorphism. Okay, 1-to-1, it's onto, obviously, because I and J goes from 0 to P minus 1. So whatever I and J, for whatever pair in ZP cross ZP that you want, you can get. So it's onto. It's obviously 1-to-1 in the way it's defined. And you just have to show that it satisfies, the homomorphism property, but that's easily done. Okay, and it becomes an isomorphism, so there you go. So we've got a lot of the groups classified now, right? We've got a lot of groups classified. We've got groups of order 2, 3, 4, 5, 6, 7, 8, 9. Right? Any P squared, 25, 49, 121. Right? They're all ZP squared or ZP cross ZP. Later on, we'll do 8. We're almost there. We can get to the classifying groups of order 8. And actually, we can classify all finite abelian groups as well. That's doable as well. That's a topic in chapter 9 that we'll definitely do by the end of the semester. We definitely want that theorem. It's a cool theorem, the classification of finite abelian groups. Okay? So that's all for the discussion today, and we'll finish up in the lecture section 8.4 and do some examples there. Okay?